This video is based on personal hands-on project experience and explains how the skill instance feature introduced in Luna the 6th enables server node graphs to invoke client node graphs, its usage, suitable scenarios, and caveats. Hopefully, it will be helpful to fellow craftspersons. As is widely known, a major pain point in the development of Miliastra Wonderland is that nearly all computation must be done within server node graphs. Even parts like user interface that seemingly could be entirely offloaded to the client have no corresponding interfaces to support this. This poses a tremendous challenge for craftspersons trying to control load when building stages. Many projects could offload AI decisions, animations, and various complex conditions to the client, but Miliastra Wonderland simply does not provide such support. So why did things take a turn after Luna the 6th launched? This video will combine some simple, practical cases published by the author during Luna the 6th to explain how they leverage client-side computing power to achieve their goals. Let us first review the current state of client node graphs. In Miliastra Wonderland, executable client node graphs are categorized as follows. Character skill node graph. This is the most complete category of client node graphs, possessing all client-side functionality, but focusing on providing interfaces specific to character skills, such as various hitbox attacks, traverse, entity list, and so on. Boolean filter and integer filter node graphs. They prohibit any execution nodes and have only one output pin, which receives the result of query nodes after logical operations and passes it to client-side features that support filters. Their functionality is very limited, mainly used for simple conditional checks. Creation skill node graph for complex creation designs, and others. These are overly complex and carry some uncertainty, so we will not use them for now. Client node graphs have one capability: send signal to server node graph. It can carry arbitrary data and be received and processed on the server side. Obviously, if the server could also invoke client node graphs, making data transmission bidirectional, then client-side computation results could be consumed by the server. Now, this possibility has become reality. Luna the 6th introduced a brand new feature, skill instance. A server node graph can create a skill instance for a character and persist it. During its lifetime, the server node graph can at any time use the cast-specified skill instance function to force the corresponding character to use a skill without binding to an actual skill slot and without requiring any player action. With this kind of interactive interface, client invocation is within arm's reach. Now we simply need to create an instance skill, attach a client node graph inside it, then instantiate and cast this skill from the server node graph, and we have client-side computation. The advent of skill instances allows server node graphs to invoke client node graphs at any time. However, we must also note that it brings many constraints and is not as straightforward as simply using a signal. First, you cannot directly pass parameters when invoking a skill instance. Therefore, any arguments or state values must be transmitted via entity custom variables. This is not just an inconvenience, it primarily introduces data synchronization issues, which we will expand on later. Second, client node graphs themselves have many limitations. The most obvious are: composite nodes cannot be created, custom variable values cannot be modified, and reference types such as lists and structures cannot be mutated. This slide lists a personal summary of client node graph limitations. Feel free to take a screenshot for reference. Let's add one more point. Client-side computation and animation skills are mutually exclusive totally. We know that a character can only perform one skill at a time, and during the execution of an animation skill, if server node graph invoke another skill instance, there will be mutual exclusion between them. If this skill is an instant skill, it would be unable to execute at all. If it's also an animation skill, the result whether the original skill is interrupted depends on the interruptibility settings of the original skill. In short, this mutual exclusion can lead to some tricky situations. We do have some workarounds, but they are not very elegant, so it's best to avoid this kind of design, like staggering the timing of calling client node graph and the periods when players can cast skills. When the duration of a single animation skill is less than 0.5 seconds, in practice, instant skill can also be normally triggered in most cases. But overall, this problem does exist and is of great impact that need to be noted in design. But for craftsperson friends who are just starting to try this strategy, the most obvious challenge is that it is an asynchronous call. This is akin to the most primitive form of asynchronous programming, entirely callback-based. After the server casts a skill instance, its logic is interrupted right there. Only after the client node graph sends back signals can the flow continue in the corresponding monitor signal event handlers. This is quite different from splitting server logic into signals. The latter at most defers certain logic to later execution within the current event, still essentially within the same time frame, whereas when invoking client-side computing, the server has absolutely no control over the client's state. The client may take a long time to respond due to latency. In multiplayer games, the player might have just disconnected. Therefore, the server can never guarantee that the client node graph's results will be returned in a timely manner, or even whether they will be returned at all. So what can client node graphs actually do? Let us look at some case studies. Let us first walk through one of my personal assets and a multiplayer stage to illustrate how it uses client node graphs. Client node graphs gained a new query node in Luna the 6th, get player movement input. Using this as a foundation, the author developed the precise input detection asset, now published on the Miliastra Wonderland Asset Center. Its key highlight is that it uses the new unit status in Luna the 6th trigger skill on timer to implement a high-precision detection system. While its highest precision reaches 2.5 milliseconds, it doesn't need server timer at all. Though the client tick frequency is very high, it'll only send signals when it detects changes in input. Its overall load is so low that can be ignored. This pattern is also made possible thanks to the skill variable introduced in Luna the 6th. It is a value shared at the character scope. The server cannot read or write it, and currently only floating point numbers are supported as the type. This is the only means for client node graphs to persist data, and we will revisit it later. The new unit status in Luna the 6th trigger skill on timer would spawn a timer in client to trigger the skill on a specified slot, but its tick interval supports a minimum of 0.1 seconds or 10 milliseconds. To have a higher detection precision, we take a new feature of skill editor in Luna the 6th, loop track. With placing 4 node graph invocations in a time span of 0.01 seconds and setting the loop count to 25, we can have an animation skill that would invoke the character input detection node graph 100 times. Due to a relatively short animation time span, though it's an animation skill and would even always persist after enabling the feature, in practice, it won't cause interference on our policy of using other instance skills to execute client node graph. This stage has been equipped with this kind of high-precision input detection, but it can also use massive instance skills to perform client-side computation without any issue, which is a strong evidence of that. A deeper use of client node graphs in this stage is offloading item spawning logic to the client. Every 3 seconds, the server casts a skill instance to invoke a client node graph, requesting it to decide item types and positions. Since client-side computing power is essentially unlimited, the node graph performs comprehensive analysis of the current field state, then decides item counts and placement. The server only needs to perform basic validity checks to prevent runtime anomalies, greatly reducing server load. In multiplayer games, a natural question arises: which client should perform the computation? The author has packaged a dynamically detect lowest latency client asset, available on the Miliastra Wonderland Asset Center. Its function is straightforward. Periodically have all players in the session send back the millisecond timestamp obtained via Luna, the 6th new node get current client time, high precision. Upon receiving the signal, the server initiates another identical call. By comparing the time difference between the two calls, a qualitative value of client latency can be calculated, essentially a two-way handshake process. Since this scenario does not require high-state precision, we can ignore data synchronization issues. However, the case study below requires some special handling. Angel's Training, published by the author, is a Miliastra Wonderland recreation of the Zenless Zone Zero event, Angels of Delusion Training in Progress, featuring a Tetris variant gameplay. By leveraging client-side computing power, we solved several pain points, such as block landing preview, simultaneous clearing of up to 15 rows, score calculation with 5 freely allocatable bonus multiplier zones, and more. The core logic offloaded in this Miliastra Wonderland stage is the chain reaction triggered by row clearing. First, the node graph traverses all rows on the field and checks whether clearing conditions are met, recording the state for every row. The descent of remaining rows is also computed client-side. Second, the stage maintains the highest block position per column for more efficient landing prediction, updated directly by the client after evaluating the post-clear field state. Third, score calculation is done entirely by the client. The server simply takes the result. Finally, the player interface displays the clearing multiplier breakdown for this action, which involves relatively complex string concatenation logic, all guided by the client and executed by the server. What problems arose in practice? First, regarding row clearing itself, obviously the game must wait for the client's result before continuing. Therefore, after casting the skill instance, the server directly enters stop the world, pausing all logic until the client reports results before the game can resume. Note that this can be problematic in multiplayer, as players may disconnect or leave, and multiplayer games demand high real-time responsiveness, making global pausing of limited feasibility. Second, data synchronization issues. We must understand that although data sync between server and client normally does not require Craftsperson attention, it clearly cannot guarantee that client state is always consistent with the server. Generally speaking, at least within the same event handler, if you modify custom variables and then immediately invoke client computation, the client will not be able to read the latest values. How do we solve this? We need to leverage the new skill variables. For example, we can configure a client-side async call sequence skill variable, and on the player entity, configure a server-side async call sequence custom variable with an initial value of -1. Before each client computation invocation, the server first increments the server-side async call sequence by 1, then casts the skill instance. When the client begins its logic, it compares the two sequence values, and only if they match does it perform computation and return results, then increments the client sequence using increased skill variable value by 1. If they do not match, it means the data version is stale, and the client sends a special signal to the server requesting a recast of the skill instance. After covering so much technical content, let me now share some practical experience from working with client node graphs. 1. Monitor signal should preferably be placed in the level entity node graph. This is actually not a constraint unique to client invocation. When writing server node graph logic with signal splitting, you also need to watch for this. If you monitor signals within player, character, or other entity node graphs, multiplayer games will cause multiple entities to redundantly receive the same signal, leading to logic errors if the signal was not designed for broadcast. 2. Do not call cast specified skill instance during the when entity is created event of player or character entities. In practice, it will not take effect. Wait about 1 second before proceeding. 3. Develop the habit of initializing all local variables at the very beginning of the node graph. A major difference in client node graphs from server node graphs is non-existent local variables and entity custom variables not predefined at edit time will not read as default value. They can indeed be used as default values in computations, but critically, using a null value as a signal parameter will cause the signal to fail to send entirely, and this kind of issue is very difficult to debug. 4. Although client node graphs do not allow list modification, if you truly need it, you can use multiple branches plus local variables to simulate. This does require significant repetition, but it is dictated by current limitations. 5. Send signals generously. This does not actually produce significant load, and there is no hard limit. The only thing that determines load is the processing logic the server performs upon receiving the signal. For example, in this Tetris's row clearing logic, a typical run sends about 40 signals, most simply modifying a value in a list or teleporting an entity. It can also handle string concatenation or other roundabout user interface logic, such as the artistic score display in the stage, which is entirely guided by client signals. Let us now wrap up with some conclusions. First, what are client node graphs well suited for? Complex AI decision logic where real-time responsiveness is not critical or some delay is tolerable. Slightly complex user interface logic such as string concatenation, asset identifier changes, and so on. These scenarios can generally tolerate significant latency, but data synchronization issues should be watched. Random events where accuracy requirements are low, or even where invocation failures can be tolerated. Other complex logic that can tolerate delay, such as statistical computations and the like. Second, what are the limitations that are easy to hit? When player is using an animation skill, triggering a skill instance is invalid. This is a very significant limitation, but I personally think the policy of client-side computation still has its practical value. Many stages would never use animation skills, while instance skills won't interfere with each other at all. No bitwise operations, this is a very significant impact. Client-side computation is very prone to floating point precision issues. It is recommended to pass floating point values as is and perform rounding on the server using proper rounding nodes. No list modification. Some simple logic may become very complex to implement. The lack of composite nodes has a significant impact, but since client-side local variables and getCurrentCharacter do not need wiring from some fixed point, you can essentially avoid Y spaghetti when writing, and with appropriate zone partitioning, create more maintainable node graphs. The sequence matching method cannot necessarily guarantee global data synchronization. At most, it guarantees that custom variable data on the player is up to date. Other entities' data may not be. Of course, if conditions do not allow resolution, you can disregard this as it is stable most of the time. Client-side computing power is very abundant and will never crash the stage, but it is not entirely unlimited. Personal experience suggests the limit for a single computation is on the order of tens of thousands of nodes. Exceeding this will cause noticeable client stuttering or even unresponsiveness. If it is not visible to the naked eye, you generally do not need to worry too much. Finally, some personal advice. Save frequently. Nobody wants to rewrite their client node graph from scratch. However, Saving in the sandbox does not equal saving in the game, and vice versa. You must save in the sandbox first, then save again within the game for it to truly be saved. Otherwise, a reconnection or crash will cause a full rollback and loss of progress. Take data synchronization seriously. Before splitting logic, you must have a thorough understanding of its data real-time requirements. If data sync issues do exist, consider using the sequence matching method for simple control. Do not overuse client-side node graphs. The invocation itself has some latency, and if global pausing is needed, it will significantly impact player experience. A better practice is, first evaluate the current situation on the server, only invoke client-side computing when truly needed. If the logic is not too complex and pruning is effective, bypass the client entirely. One more reminder, signal parameters must not contain null values, that is, non-existent local variables, or the signal will completely fail to send. I personally believe that with the iterative improvement to Miliastra Wonderland's user interface and client-side computation support, we have truly entered a brand new era. I hope this video has been helpful, and I wish all Craftsperson success in creating outstanding, popular works.